All right, so I'm streaming already. Okay, guys, my computer, the mic on my computer is not quite as directional as the wireless mic, so it doesn't pick up my voice as well as the other mic. Basically, it picks up all the sound in the classrooms almost equally good. So that means when you guys are talking, it will pick up your talking as well. So that makes it kind of difficult to make my voice stand out in the recording. All right. So let's go ahead. How many people want me to go over the swap subroutine solution? Okay, we got a few hands. Okay, we can do that. That's not going to take a whole lot of time. What about Fibonacci? Okay, we got more people. Okay, so we'll do that first. And we'll start with, okay, I need my old person click on so I can see what I'm clicking on. There we go. Oops. All right, so let's gonna resize it. There we go. Okay, so we're gonna start with the swap subroutine. Okay. I don't even need to open the homework assignment. I kind of know what the swap subroutine should look like. So we'll go ahead and look at the C code, and then we'll take a look at the assembly code. Kind of do a side by side. Okay, and we can restore pages. That's fine. And where's my? All right. So the swap subroutine looks like this. Okay, so we have swap. Okay, are you guys okay? I mean, if you guys want to talk, that's okay. Just not in the classroom. Are we good? All right. I respect your freedom. Just not in this classroom. Well, technically, it's not when your freedom or what your action can do is interfering with the learning of other people. So that's that's the bottom line. All right. So this is the way we set up the swap subroutine. T gets whatever P1 points to, P1 gets whatever P2 points to, and then P2 gets back what T has. Okay, that's the swap subroutine. And then we'll go ahead and write the assembly code corresponding to this. And we'll do it line by line. All right, so swap is the entry point of the subroutine. And we can do this using the new way of doing things, which means we can give labels to everything. So the way we do this with labels is we can say P2 is the highest item on the stack, and then we have P1 being right next to it, and then we have the return address right below that. And the last thing that we have on the stack is the local variable T. This is what we want the stack to look like. This is also called a frame. So combining all the local variables, the parameters, the return address, and a few other things depending on the architecture, it is called a call frame, or in short, it is just called a frame. So in this case, we can now define labels corresponding to these things. We can say T equals to 0, okay, T colon 0. Returned address is now 1, oops. And then we have P1 being 2, and then P2 being 3. Now, these label definitions do not do a single thing in terms of runtime behavior. All we are doing here is to equate the symbol T to mean the numerical value of 0. That's all it's doing. So from here on, if I use the label T, it is the same thing as using the literal constant of 0. That's all this is doing. So it doesn't crank out any code. It does not do anything to the stack at all. It is just defining symbolic names. So what we need to do first is to decrement D. So now we are actually allocating space for local variable T. So now we are done with line 3 of the C code, and we are moving on to line 4 of the C code. Line 4 of the C code is starting with P1, so we need to get to P1. So if you want a very structured way of doing things, this is how you do it. load A with P1, which is the offset of P1 from where the stack pointer is pointing to, and then you add the stack pointer to A. So now A is the address of P1, the parameter. We have to do a load, LDAA. That will make A actually the pointer itself. It points to somewhere, in memory. And then if we load it one more time, then A is finally whatever P1 is pointing to. So there are two dereference that is necessary in this case. And then we are supposed to store that into T, but who is pointing to T? The stack pointer. The stack pointer is still pointing to local variable T. Local variable T because it was the last item that we allocated on the stack. So that means stda is going to store whatever P1 has into T. So that's the first statement. The second statement starts with P2. So I'm not even going to bother to reuse any of the registers because I could have done something like that. When we have P1 here, I could have saved P1 into another register to kind of save myself some work here later on. I'm not going to do that, okay? So we'll start with P2 this time and do the same thing as before. LDAA. This will make register A P2 itself, the pointer. And then if we do this one more time, if we dereference one more time, then A is finally whatever P2 is pointing to. We want to store this to whatever P1 is pointing to, right? So we have to use another register because register A is storing whatever P2 is pointing to. So we use register B for this purpose. And go through pretty much the same exercise except for one step. We still need this step here. Okay, these are supposed to be B's. There we go. But we can stop here because the second dereference is a store instead of a load. Because when we get to line 24 of the assembly code, register B has pointer 1. And we need to store to what pointer 1 is pointing to. And that's why the store instruction on line 25 is dereferencing register B as the destination to store whatever register A has, which turns out to be whatever pointer P2 is pointing to. So are we good with the second line in the C code or line 5 in the C subroutine? Okay. And then the last one is to retrieve something from T and then put it into P2, whatever P2 is pointing to. So we'll do it exactly the same order, okay? Whatever D is pointing to is T. So A is now whatever T has. And then we do the same thing, LDI B with P2 this time. Add AB, BD, and then we load B from B, dereference. So this will get me P2 as a pointer, the parameter itself, and I need to store to whatever it's pointing to. So another ST instruction to whatever B is pointing to is going to get a job done. And so this will conclude the last step. We need one increment D to deallocate the local variable T. Now we are ready to return. Now if you look at swap, it has a void return type, which means it has no actual return value. For anything that has no return value, you can use register A if you want to specify the returns action. So I can do that here. I can say load A with whatever D is pointing to, because at this point, D or the stack pointer should now be pointing back to the return address because I just incremented the stack pointer. And then the rest is just to deallocate the stack pointer, deallocate the return address from the stack, and then do a JMP-A to return to the caller. And now it's all done. Okay? So the key to how I'm going to grade this assignment is to look at your code and see whether you play by all those rules. In other words, you only get the parameters through the stack. You do not make the assumption that you are swapping, location 255 with location 254, because some people did that. Okay, that would not be a correct implementation. Yes.
So since this is a void function, it's not a problem that we put the return address into register A instead of a returning value.
That is correct.
Okay.
Yep. because the caller is not supposed to interpret register A as a return value. So is that okay? Okay. All right. So that's the solution of the swap subroutine. And now we can move on to the solution of Fibonacci. Okay, the funny thing about the Fibonacci program is during the lab time of last Thursday, I actually, recorded something, because some people went to the lab, and I recorded, a, short clip, like about half an hour, to explain, how to save the return value of the first call, and then how to combine it with the return value of the second call. And I recorded, I pushed it onto YouTube, and I released it on basically the same day. So hopefully that was helpful to people who watched it. Okay, so here's Fibonacci. We'll write the C code first. So let's say it returns an unsigned integer. This is Fibonacci. It takes only one single argument, n. And I'm going to use the ternary operator. So return if n is less than 2, then we just return n. Otherwise, we return f of n minus 1 plus f of n minus 2. And that's it. Okay, so this is the C subroutine. And now we'll write it in assembly. So let's open another new tab here. All right, so this is F, this is the entry point. The stack looks a lot nicer in this case because we do not have any local variables and we only got one parameter on the stack. So we really only on the stack we have n, and then we have the return address, and that's pretty much all we have here. So now we can write the subroutine. We have to get n first and compare it to 2. So we have to do a LDIA with, let me define n first. So n is 1, and then the return address is 0. Okay? Because we are basically defining the displacement of these items from where the stack pointer should be pointing at the entry point of the subroutine. Okay, so that's why I define these things this way. And then the first thing we need to do is to do LDIAN, add AD. So now A is the address of n, and then we have to load A with A indirect. So now A is actually the parameter n, and then we can compare it to 2. We got extra registers this time, so we'll load B with 2, and then we do the compare. So we'll do a CMP AB, which is comparing parameter n with the constant of 2. So if it is less than, we go to the then portion. If it is not, we go to the else portion. So the way we do this is we only have JLI or JCI. We do not have the inverted version of that. So you really don't have a choice but to say JCI to the then branch and then JMPI to the else branch. Because JCI is appropriate in this case because it is unsigned integer. If it is signed integer, then you will use JLI, okay, and not JSI. There's a big difference between JSI and JLI. All right, so now we define the labels. This is then, and then always needs to jump around the else branch. So I'm gonna have to JMPI to end if, and then end if is gonna be at the very end, and then we have the else branch here. So this is the way I like to write my code, is to do the structure first, and then I go back to fill in the actual operation within each branch here. So I make the skeleton first, and then I flesh it out. In the then branch, which is corresponding to only this part, is I need to get n into register A. But guess what? It's already there, so I'm done. So nothing to do because register A already has parameter n. But I'm not gonna optimize this code and go like, oh, JCI can go straight to n if. I'm not gonna do that, okay? Because I can just preserve the meaning of the original code, and I don't risk, making that optimization and running into a problem that I did not anticipate. Okay, the else branch is the difficult one. Okay, so so if you ask yourself, okay, you're given the code, some kind of code like this, what do you need to do? Well, you don't really have much of a choice, right? You have to compute n minus 1 first, push it on the stack, call f. When f returns, then you have to push n minus 2 on the stack, call f again. So that's pretty much the sequence of doing this, and there's really not a whole lot of options. Okay, so we'll do it exactly in that order. So LDI AN, assuming, well, A is already in, has N, so I'm going to be a little bit lazy here, okay? But when I'm lazy, I remind myself why I can be that lazy, okay? Because 1 week from today, I can be reading this code and not be able to figure out what am I doing here? Why can't I use that register? Because register A already has parameter n, okay? So I have to write it to remind myself that. Okay, so what do I do is I need to decrement it. So decrement A. So A is now n minus 2. Push it on the stack, which means decrement the stack pointer and store to whatever the stack pointer points to. So now n minus 1 is pushed on the stack. Next thing to push would be the return address. So LDI A again, dot 6 plus, and then decrement D again, STDA, and now I'm ready to branch or call the subroutine that I want to call, which is F, okay? When I return, which should get back to line 25 in assembly code, I got 2 things to do. The first thing I need to do is to deallocate the argument from the stack. Remember, it is the call least responsibility to deallocate the return address, but everything else, including all the arguments, would be the responsibility of the caller to deallocate. So now I have to deallocate n minus 1 from the stack, which means I need to increment the stack pointer. And then right after that, I need to save the return value of this call. Because if I don't save register A at this point, register A is going to be overwritten by the second call to F. I cannot put it into another register either, because whatever register I am using to save it is also going to be used by the recursive call, because the recursive call is calling the same subroutine. So the only safe place to put the return value is on the stack. So that involves decrementing D again, and then STDA, and A being the return value. So I'm saving the return value of f of n minus 1 on the stack. And somebody can point out and say, wait, hold on a second here. Line 25 and line 26 combined is doing nothing to register D. You're absolutely correct about that. In other words, if you want to, you can comment out both of those instructions, and it would do the same thing, because one decrements, one increments, they cancel out each other. Okay? But I do want to kind of point out that technically speaking, you do have an increment to deallocate the argument, and then you have a decrement to reallocate one spot on the stack to save the return value of f of n minus 1. So even though we can optimize and say, these two can go away because they cancel out each other, but technically speaking, we do have those 2 operations, because conceptually, they do not belong to the same thing. One has to do with arguments, the other one has to do with the return value. So are we still doing okay at this point? Okay? Yep.
So where you did dot 6 and then plus, is it more proper to do it that way, or could you also just do the
You can do the label thing.
label thing?
Yep, you can do the label thing where you put a label definition on line 25 and then refer to that label over here. It would be identical. I don't like the label approach, because the label approach is prone to using the wrong label, especially when you copy and paste code. Then you can forget to update the label, because that label already exists, right? So if you forget to update the label that you refer to, then it will be branching to the wrong spot. And those bugs are really difficult to figure out, because the call is fine, it just returns to the wrong spot. So from the standpoint of making my code a little bit more less error prone, I prefer to do it this way. Okay, next thing we need to do is to call f again, but with n minus 2 on it. So at this point, somebody is going to say, but Tech, can't previous argument into another register and then just reuse n minus 1 and decrease only one more from that and call it the argument of the second call. I could have done that, but there's no guarantee that the subroutine is not messing around with the parameter. Okay? So I cannot technically do it. Okay? So in this case, because I'm careful not to do it, I can, but in general, you cannot. The only time you can sort of do that is when you have a const here. If you have a const here, you're telling the compiler that the argument or the parameter would never be changed by the subroutine. Then you can sort of do that. But even that is not a guarantee. Because what you can do, okay, so this is not a part of the code, but I'm just illustrating you can do something like this. Not a good idea, but it can be done. You can actually cast n back to a non-const. Then you can do whatever you want with it. That is actually legitimate. You can unconst something. Now, why would you want to do something like that? I have no idea. But it is legitimate. At least last time I tried this, it was actually doable. The compiler would not complain. Now, if you do not do the casting, if you do something just like n++, the compiler would catch this and say, you're not supposed to change something that is already const. But you can cast something that is already const into non-const, and then you can change it. Okay? So not a good idea to rely on the argument, because the subroutine could have changed it. So that means at this point, I have to recompute that local variable, the parameter, from as an argument that was passed to me. All right, so we'll do exactly the same thing as before, LDIA with the name of the argument, which is n, okay? And then we say add AD, just like before. But this time, this is not right anymore, because we have one extra thing sitting on the stack at this point that was not there when I made the assumption that n is only one byte away from where the stack pointer is pointing to. Yes?
Yes, I have a question. It threw me off completely. Line 24, John, you have f is all the way to the top,
Mm-hmm.
right? You have to re-execute all that code again, right?
Okay.
That's what I got here.
In your mind, okay, in your mind, think of it like this. This is f of f1, this is f2. Then, if in that case, would it be okay for me to do this? Yes?
Existed, right?
If they were different. So what makes it impossible if they were exactly the same?
Where does the code continue? That's what I'm trying to.
Say that one more time.
Okay, what's the next step in the code? Does it go out?
The next step of the code, it will go back to the label f.
Okay.
It will go through this code again.
Okay.
And then depending on whether n is less than 2, if n is less than 2, then it's going to go through the else branch, the then branch, and then it just returns with the value of n. And where does it return to? What do you think it's going to return to?
Not the IA plus 6.
It's going to return to here. In other words, okay, so you bring up a very good, interesting question, which is, does recursion require special attention when we are implementing a recursive subroutine in assembly, as opposed to just calling another subroutine? And the answer is no. Okay? Recursive subroutine calls do not require any special attention. It is not different from any other call to any other subroutine. We play by exactly the same rules regardless of what you're calling. Is that okay? So it does seem like it is a loop, but it is not a loop. It is calling itself, which has certain attributes of a loop, but is not exactly a loop. Okay, so getting back to here, we have a problem because the stack pointer is now pointing to the return value of f of n minus 1 that we saved on the stack. 1 byte on top of that is the return address, and then 2 bytes on top of that is parameter n. So that means our n is actually not correct anymore. It is not just 1 byte away from where the stack pointer is pointing to. We can just adjust that. We just say whatever n is, which is 1, add 1 to it to account for that 1 extra byte that we have just pushed on the stack. So this is important. So A is now the address of n. We do LDAA. So the A is now actually n. Then we decrement it twice. And then we call the subroutine again, push it on the stack. So that means we have to decrement the stack pointer, stda, to store the value of register A to where the stack pointer is pointing to. And then we save the other return address, .6 plus, decrement the stda, jmpi to f again. This is the second recursive call with n minus 2 as the parameter. When it comes back, the first thing we need to do is to increment d to get rid of the argument that is on the stack. So we say deallocate argument on the stack. And at this point, okay, right at this point, the stack pointer is pointing back to the return value of f of n minus 1 that we pushed earlier on the stack, which is very handy because we actually need it now. Because we need to add the return value of f of n minus 2 to the return value of f of n minus 1, which is now sitting on the stack. The stack pointer is pointing to it right now. So we do a load instruction, put it into another register, anything but A or D. So B is now the return value of f of n minus 1. And remember to increment the stack pointer because it is of no use to us now. We have to deallocate the saved return value from the stack at this point. And then we can add AB, sorry. Because register A still has the return value of the call of f of n minus 2. So combining that with B, which now has the return value of f of n minus 1, we have the result that we need to return. Is that okay? All right. So at this point, we have nothing else to do except to return back to the caller. So we have to LD again. This time we have to use we cannot use register A because the Fibonacci subroutine does return an integer. So we have that in register A already. But we can use register B. Okay, so we use register B to specify the return address, increment the stack pointer because it is the call lead's responsibility to deallocate the return address from the stack. And then we have a JMPB, and that's it. That's the Fibonacci program. Yep.
What about the case where it returns the parameter, just the parameter itself?
That was handled in the else case. So that was done, you mean this part, right?
Yeah.
Yeah, so that was done way early. And I said nothing to do because register A already has n. Yep.
But don't you need a return? Don't you need to return out of that?
It jumps to end if. Oh, thank you. I do have end if, it's just at the wrong place. You are absolutely correct, the end if should be here. So they share the same common code to actually go back to the call. Thank you. So, do we have any questions about the solution of this program? Yep.
I guess the only part I got is that is the line where it says line 38 versus GMPIF.
Line 38,
Yeah.
JMPF.
Yeah.
It's part of a call. So the call technically starts from, okay. So the call technically starts from here. Line 28 is the beginning of that call. This is where we read back n, decrement n by 2, we get n minus 2. We push that on the stack. Then we push the return address on the stack. Then we continue execution in the subroutine. When we return, we deallocate the argument. So this, technically speaking, from line 28 to line 39 of the assembly code, technically is f of n minus 2. That is the call of f of n minus 2. So it would be a good idea to, I'll try to remember to save this program and upload it so that you guys have a chance to examine and comment it. So that would be my recommended activity, when you have time to investigate this program. And you should run it too. You should run it and double check and make sure that it does work correctly. I'm almost 100% sure it does. So are we good with this particular program? Yep.
Can you explain line 28 and 21? There,
21?
21.
You mean this one?
Yeah.
Oh, okay, I see.
Why that?
This is something that we have been using for about a week or two or so. The dot is representing the address of the LDI instruction, and then this is the postfix notation of adding 6 to it. So when you add 6 to LDI instruction, so let's say this is location 0, okay? So offset 0. So 0, 1 would be here, 2, 3, and then 4, 5. So off by, so 6 bytes away from the LDI instruction would be the address of the ST instruction, which is where I want the subroutine to return to. So this is equivalent of putting a label definition between line 26 and line 27, and then refer to the label instead of .6+. It just means that I do not need to define a label, for the return address. But it's a feature of the assembler that I have added in the previous semester, and we kind of talked about it for one or two classes. Is that okay? All right. Yep.
If it was a 7 instead of a 6, it would return to the LDI below the
Yes.
IP.
So if you change this 6 to a 7, then it would return to the LDI instruction, which would make it very confusing because, well, it's not confusing, it's just really bad because we would not have saved the return value from the subroutine call, but the stack pointer is still pointing to the same place. So you'll be using the argument instead of the return value to add, and so the result will be wrong. So are we doing okay so far with this code? Yes? Yep, go ahead.
All the way up.
All the way up.
Can you explain a little bit more about line 4 and line 5?
Line 4 and line 5 are defining the labels and return address to exactly what the constant is, or whatever the expression is to the right hand side. So when I refer to n, I'm actually just referring to 1. When I refer to return address, I'm actually referring to 0. And I never refer to return address, I just put it here so that I get a good idea of what is on the stack, or what the stack pointer is pointing to. They are just labels. I mean, they are just symbolic names, with a particular numerical value. Is that okay? All right. Any other questions? No other questions?
Are you gonna put that code today?
Yeah, let's do it now, before I forget. Because I have a tendency of forgetting important stuff, right? The more important, the more likely it is forgotten. Last week, over the entire weekend and yesterday, I thought I lost my keys to my bicycle lock, to the classrooms, to a lot of things, right? And I could not find it at home. I could not find it in my pants, in the pockets. I could not find it in my backpack and whatnot. And today, after I got my bike locked at the bike locker, I found the key. It was still attached to the lock of the battery of my electric assisted bike, because I needed that to put the battery back on Thursday night on my way home, and I forgot to take it out of the keyhole, and it was attached to that whole thing the whole time. Yeah, that's basically how absent-minded I can be. And I keep surprising myself too. So this would be called Fibonacci, right? Fib.ttpasm. There we go. And then switch to the browser, go to So I'm gonna send it to you guys as an announcement, which means if you do not get the email or you lost the email or you accidentally delete the email, you can still go to the class website and go to the announcements and get it back. So the idea of the extension TTP-ASM is it stands for Text Toy Processor Assembly, which it means it is the source code to be assembled by the assembler. Okay, if you're using Windows and you cannot open this file, you can just rename the extension to TXT because it's just a regular text file. But then Notepad will be totally confused because the way the end of line is specified is different in Linux compared to DOS. So I would advise you to open this using WordPad, which should come standard, with all versions of Windows. Yep. Notepad++ will open it. Okay, there you go. Because I think I got that question a few times. There you go. So you should have it now. All right. So moving on to new topics. Are we ready, or do we still have more questions regarding the Fibonacci or the swap subroutine? No questions? Okay. So let's go ahead and look at some C code first, and then we'll look at the assembly code corresponding to that C code. So this time we're going to look at structures. Okay, so we define the structure. Let's call that X, okay, because it doesn't, I don't know what purpose it serves. I'm just going to define it. So we have uint 8_t X, and then we have int 8_t Y, and it's an array of 5 elements. And then we have uint 8_t Z, like that. Okay. So this is how we define a structure. A structure is no different from a class in C++. Other than every member of a structure is by default public. Okay? And in C, you cannot have methods defined within the structure. So you cannot have like a subroutine defined inside the curly braces. And you also need a semicolon after the end curly brace, where in class definitions you do not need that semicolon. Other than all of that stuff, it's kind of like a primitive class, if you will, okay? Because the struct concept existed before class. Class basically evolved from struct. So is that okay? All right. So I'm gonna write a subroutine here. So we got main, and so in main we have an actual structure definition, struct X. Let's call it var1, and then we'll call a subroutine called f again. We'll pass the address of var1 to f, and that's the end of this entire thing. And this is f. F as a subroutine is expecting a struct X pointer, and what it wants to do is to initialize it. Okay, so we'll go ahead and initialize the member X, lowercase x, to, I don't know, 10, okay? And then we'll initialize y bracket 0 to 0 because it's now terminated as a string, and then z is going to get a value of 15. Okay. So do we have any questions about this C code? It should be fairly standard, and cisp310 should have taught you all the concepts already. So are we good so far with this code, which is strictly in C? Can I take the silence as yes? Okay. The default value, right? Silence equals yes, true, not 0. Okay. So now the question is, how do we implement this code? Well, okay, I'm gonna be kind and ask this, but only once. Is everybody familiar with this symbol? Yeah. Points to? Yes? Okay? Alright, that's good. Because occasionally I have people who have only exposure to Java and they go like, what is that? Yes?
Does it return anything?
F is has a void return type. It doesn't return anything. Okay, so if you ask the question, then let me follow up with my own question. So what does F do? Does F serve a particular value in the program like this?
F just visualize values to the array and look at whatever inside the struct X.
Okay, so what is struct X? What is line 1 to line 6? Does it use up RAM space? Does it use up instruction space? What does it use up when we look at just line 1 to line 6? What kind of resources does it use up in the program? It's a trick question, but
It doesn't use anything to like
Hmm?
it doesn't use anything to like make something else.
Exactly, it does not use anything because a struct definition, like a class definition, is a template. It is like a cookie cutter, okay? So line 1 to line 6 is a cookie cutter. So if I just give you a cookie cutter and I'm asking you, how much cookie do you need? Cookie dough do you need? You will say, I'll be making cookies. I mean, this is just a cookie cutter. So line 1 to line 6 is only a cookie cutter. It's not cookie. You cannot eat a cookie cutter. You cannot bake, well you can, but it doesn't serve you any good, baking a cookie cutter. Okay, if you're a bender, you can even eat a cookie cutter, but as a human, you cannot. Is that okay? So where did I allocate cookie dough to make my cookie? Okay, first of all, in the execution of this entire program, how many cookies were made? There was only one cookie, very good. And where is it made? Line 10, very good. So line 10 is the allocation of the space on the stack, allocated cookie dough, and use struct X, which is the cookie cutter, and go like that. Okay? What does it do? What does the cookie cutter do? It says, okay, you give me a bunch of cookie dough, and now it has a shape. It has got a member called lowercase x, it has got a member called y, it has another member called z, and the first one is 1 byte, the second one takes up 5 bytes, and the third one takes up 1 byte as well. Is that okay? But that cookie didn't last very long, because when we get to the end of the main program, because var1 is a local variable, it gets deallocated. So that cookie gets crunched up and get back into the big cookie dough pool to bake other cookies later. So are we good so far? And most of you will only remember cookies, but not anything about structures. And if I were in your place, I'll be thinking about chocolate chip, oatmeal, all the various, all the different kinds of cookies right about now, because I'm already doing it in my head. Okay, so let's take a look at the assembly code to implement something like this, okay? Because this is going to be a little bit interesting, and it is also going to be relevant to your lab for tonight, okay? So this is good stuff for the lab tonight. So how do we define a structure in assembly code? It's like, what? I mean, what is this, what is this thing here? How do we define something like that? So the way we do it is we look at the displacement of each member of a structure from the beginning of that structure. In other words, we look at member X and we ask, how far is member X away from the beginning of a struct X? What do you think? Is the first member Yep. I thought you had an answer. It's the first member. So what do you think is the displacement of the first member of a structure from the beginning of the structure? Yes. 0. It's right at the beginning, but you're close. You've got the right idea, except we count from 0. Yeah. So it is 0. Okay. So we say, okay, member X is 0 byte away from the beginning of a struct X. What about member Y then? Member Y is right after member X, and member X takes up 1 byte. So where do you think member Y is relative to the beginning of a structure? It's 1 byte away, right? Because that 1 byte was used up by struct X. Member X. What about member Z then? It'll be 6 bytes away from the beginning because member X took 1 byte, member Y took 5 bytes. 1 plus 5 is 6. So member Z will be 6 bytes away from the beginning of the structure. And how big is this structure? If I make a cookie using this cookie cutter, how much cookie dough am I taking? 7 bytes. Okay, very good. Well, it sounds like we can understand what a structure is and express everything as a number, right? The offset of 0, the offset of X is 0, the offset of Y is 1, the offset of Z is 6, the size of the entire structure is 7. Those are all numbers, right? So what we'll do to define the structure is really just using labels and numbers. So my personal way to do this is to say X, okay? The first X, uppercase X, refers to the name of the structure, and then the second X refers to the member X, okay? And this is the offset of that thing from the beginning of a struct X, which is 0. And what do you think this should be? 1, very good. And what about this? 7, okay, very good. Is that 7? Nope, it's 6. Okay, the next one is 7. The size of a struct X is 7. That's it. That's how we define the structure in assembly code. And you guys go like, but you're just defining a whole bunch of labels. And you're right. You're absolutely right. A structure is no more than just a bunch of labels when you're doing in assembly code. Because no assembler that I know of understands structures. Okay, it cannot parse the syntax of a structure. So this is the next best thing you can do to represent a structure.
So this is a template as well.
Huh?
This is a template as
It's
well.
a template, yeah. Yep. Go ahead.
What was the size for it?
Hmm?
What was the size for it?
We'll see. When you make a cookie, you have to measure how much cookie dough, right? That's when we need it. So are we still good so far in terms of concept? We just need to know the displacement of each member from the beginning of the structure, and we kind of need to know the size too. So the other way to express this, which is the way that I prefer, is we refer to all of these things relatively. I prefer to do it this way, because this way, if I decide to change the size of something, like if I want to allocate 50 bytes instead of 5 to Y, I only have to change one thing, because they're all relative. Yep.
For example, if in Maine, in our code, C code, in Maine we have 2 structures, X and Y.
Okay.
So basically, we need 2 templates, right?
Well, let's do it. It depends. No, you can use one template to make 2 things, right? So it depends on whether, are you talking about something like this? Okay. So let's do it this way. Leave one variable totally unused, okay, which is fine, okay? So are we okay so far with the C code of how we define a structure as opposed to the assembly code of how we do pretty much the same thing? Are we good? Okay. So now we can get into Maine. Now Maine doesn't really is a thing in assembly code because we always start execution from location 0. And this is something that I always do, which is also not necessary because the stack pointer, register D is always starting at location 0 when we reset it. Okay, but I'm going to put it there anyway. All right, so now we need to allocate. We need to allocate some space for var1, and we need to allocate some space for var2. Okay, first of all, where do we allocate that space from? The stack. Because var1 and var2, they are both local variables. If they were global, then they would be allocated somewhere else. But I'm not going to do any global variables. So we need to allocate that space. So I'm going to write down what I want to do, then we'll talk about how we do it, okay? Allocate space for var1, okay? So we'll do the allocation based on the ordering of the variable in the C code, okay? How do we do this? What do you think? Okay, first of all, how much space, how many bytes do you think var1 is going to take up? 7 bytes, okay. So, how about this? Hmm? No. Why not? How is this approach bad? It takes a lot of space, okay, but that's not the only thing that's bad about it. Yep.
What about when you need to allocate space for the array?
Exactly. And also, it's not sensitive to x underscore size. If I change the structure, if I do something like this, like 7 decrement D, it's not going to work if I change the structure itself. So the best way to do this is to do something like this. LDI A or B or C, doesn't matter which one in this case, x underscore size, and then we say subtract from register D A. Now, if I decide to change and go like, oh, I want to add a few more members into struct X, and I change all of these definitions accordingly, done. This code is not sensitive at all. Okay? So the whole idea is we try to use symbolic names so that we do not have as much direct reliance or dependency on the structure itself. Okay. Well, if we subtract it again, then we're now allocating the other one, right? Now I could have done something like this, okay, and then only the allocated ones, okay. But I'm not going to do it, okay. I'm going to do it this way so that it's clear that we are allocating for var1 first, and then we're allocating for var2. Okay, so we have allocate var1, allocate var2. Is that okay? Yep.
Could you do LDI A, comma X underscore side? And then never mind. Sorry.
Okay. All right. Because that's exactly what I did.
I was thinking something else.
Okay. Okay. So, but what is the offset of variable 1 and var1 and var2 relative to where the stack pointer is? Those are the only two things that I need space for Maine. So now I can say, if I know where the stack pointer is, where's var1 and where's var2? What do you think? So what is the stack pointer pointing to? var2. Okay, so var2 is pointed to by the stack pointer. And then where's var1 then? That's right. You're absolutely right. So that means if I want to use labels to remember where var1 and var2 are relative to where the stack pointer is pointing to, then I'm going to define those things like this, right? I'm going to say var2 is 0 because the stack pointer is pointing to the beginning or the first byte of var2 right now. And then var1, excuse me, is var2 x underscore size plus. But why don't you just say 7? I mean, this whole thing just computes to 7. Well, if I used 7, like the number 7 here, then if I decide to change the size of the structure or change the membership in the structure, then this code is not going to work anymore. But if I stay consistent and do it this way, then everything is relative to each other. If I want to add another var3, it would be pretty easy. I just need to insert var3 is 0, var2 is blah, blah, blah. But var1 doesn't need to change anymore because it's only relative to where var2 is. Is that okay? All right. Okay. So we got the labels defined, and now we can call the subroutine. To call the subroutine on line 12 of the C code, we have to compute the address of var1. Okay. So we'll do it the standard way. Okay. We'll say LDI register A with var1, add AD. So now A is the address of var1. Do I need to dereference? Because it seems like we always dereference when we get to the address of something. Nope, this is what we need. That's what the C code wants. We want to pass the address of var1 to F, and we already have it in register A. Okay? So the next thing to do is just to push it on the stack, which means we decrement the stack pointer, store to what the stack pointer is pointing to, register A, which is the address of var1, because var1 takes 7 bytes. It doesn't fit in one register. We have to be pushing the address of var1 and not var1 itself. Okay? Then we push the return address, which is LDIA .6 plus. Now remember, the .6 plus needs a space between the dot and the 6, and another space between the 6 and the plus, because that's how the parser works. It needs separators to separate the operands. And then we have decrement D, allocate the space, store to what D points to, A, and then JMPI to the subroutine F in this case. And when we get back, we have to increment D, because that's the argument that is still sitting on the stack. And then we have to deallocate the local variables, which is the reverse of what we did earlier. We have to do an LDIA with x underscore size. And then this time we're adding that back to register D instead of subtracting from register D, because we have to balance the stack, because at the end of a subroutine, when we get to the end of a subroutine, everything that is a local variable needs to be deallocated from the stack before we can get back to the return address. Now, Maine does not really have a return address, but I want to do the same thing anyway. Okay, so this way we don't forget to do it when we do need to do it. Now, normally for any other subroutine at this point, I'll be loading whatever the stack pointer points to into a register, increment the stack pointer, and then JMP whatever the register is as a normal sequence of returning. But here, because Maine is not actually called by anyone, there's no place to return to, so I really don't have a choice but to specify a halt instruction to say, okay, we're all done, stop. So are we good with Maine at this point? Mostly how we deal with the allocation of a structure and how we compute the address of a structure, which is no different from computing the address of a local variable or a parameter that is a scalar. Are we good so far? Yes? Okay. So we get to F now. And what is on the stack? Well, we got parameter P on the stack, and then we have the return address. That's pretty much it. So from the perspective of what is on the stack, it's not that complicated. P is 1 byte away from where the stack pointer points to, and then the return address is 0 byte away from where the stack pointer points to. Pretty simple step. What makes it kind of complicated is, how do we do something like that? The right hand side is easy, just a constant of 10. The left hand side is member x of what P points to. How do we get there? Well, let's do the easy one part first. LDI A10, okay? That's my right hand side. So I will even comment it and say this is the right hand side of line 18 of the C code. Okay, so how do we do the left hand side? What do you think is the first thing we need for the left hand side?
Well, we have the address already from the parameter on the stack.
So we need to get to the parameter first, right? Parameter P, right? Okay, so how do we get to parameter P? LDI A with P, right? And then add AD. So now we have A being the address of P. Then what do we need to do? Yep.
I think you might want to use register because you just overrode the 10.
Huh? Oh, right. Okay, register A has 10. Okay, thank you. So let's change this to register B. There we go. Yep, okay, thank you. So register B is now the address of the parameter. So on line 18 of the code, do we want the address of the parameter or do we want the parameter itself? We want the parameter itself, right? Because it is whatever the parameter points to.
Wouldn't store do that though?
Huh?
Doesn't store already do that?
Store can do that, but I'm not storing to what the pointer is pointing to. I'm storing to a member of the structure pointed to by P.
But x is plus 0.
You don't know. I don't know how far x is away.
Yeah.
I could, the idea is you don't want to make any assumptions, right? You just use the label. Whatever the label is, use the label, because later on I could insert another member in front of x. Then if you make that assumption of, oh, the beginning of the entire structure is x already, your code is not going to work anymore. So we cannot make that assumption. Yep. Okay, but from here, I know the address of P at this point. What else do I need now? I need to dereference it. I need to first dereference it because B is only the address of the parameter. But I need the parameter. I need to know what the parameter is pointing to. So we need to dereference it once at this point. So the B is actually parameter P. Now what is register B pointing to? Register B is pointing to the beginning of a structure. But I don't need the entire structure, I just need one member of the entire structure, right? Where do I find that member? X underscore lowercase x is the label that tells me how far off the member is, away from the beginning of the entire structure. B, register B is pointing to the beginning of the entire structure. I just need to add x underscore x to register B to get to the member that I need. Is that okay? Okay, let me do this first and then we'll go ahead and take a look. Is that okay? So what would be helpful after class is to draw a picture, okay? Actually, we'll run this code, okay? I think we got enough time today to run this code. So when we run this code, we'll do the trace analyzer thing, and then we can actually visualize what is happening on each line of this code. What else should I be doing with register B? B is the address of member X of the structure that is pointed to by P. And what am I going to do with it? Put a 10 into it, right? And the 10 is already in register A. So that means at this point, I just need an STBA. Is that okay? Now, the other lines would be pretty much the same thing, except I have to change the member that I need to access. So there's nothing new with the other lines, right? So let's just say that we are doing line 20. I want to change. Well, okay, maybe I'll just copy and paste this. So this is the second line, which is accessing member Y. So member Y is here, and I want to change it to 0 instead of 10. And then we move on to the last line, which wants to initialize, oh, okay, crap, where did I, there we go. So we want to change this to 15, and we are storing to member Z instead of member Y. Okay, so we're all done. Now we can return LDB, A is fine in this case. Increment D, JMPA. That will be the end of the subroutine. Okay. Are we doing okay or not? I mean, the comments obviously are off. This is line 20. This is member Z. And this is line 19. And this is Y bracket 0, which is the beginning of the entire array. But otherwise, it's the same structure of code. Yep.
In this particular assembly code,
Mhm.
are we talking about struct x variable 1, or it doesn't matter?
Well, because we're passing the address of var1 to the subroutine, then we are only working with var1. var2 stays uninitialized.
Right, but if we would work with var 2,
Mhm.
I think line 56 would have to be changed, right?
Nope. It's the same subroutine. The subroutine is insensitive to how you allocate the structures. It's basically saying, give me a piece of cookie with this shape and I'll do something to it. So as long as the cookie that you give to subroutine F is of a particular shape, subroutine F will just go like, okay, I'm going to cut off this part, add some part, add a raisin to this part, and so on. That's all it's going to do. All right. So we got some time, so we'll go ahead and copy this and go into the assembler, which I think is still around. Okay, and then we go to RAM file just to make sure that we don't have any errors. No errors. Okay, that's good. File. Oh, okay, one more thing. If I want to use the trace analyzer, I would need a no op instruction at the very beginning. So I need to put one no op here. Okay, that's okay. The assembler is pretty quick. There we go. I'll call this struct.csv. All right, so now we got it saved. We have a choice. You have a choice. Do you want to run this in the simulator in a GUI mode, or do you want to run it in the non-GUI mode and look at the trace instead? In other words, do you trust me and just want to look at the end result, or do you not trust me and want to actually see how the whole program works?
I'm okay with that.
Huh?
I'm okay with that result.
You only want to look at the end result? Okay, we can do that first. Okay, so we will look at the end result first. So let me look at the history and find out which one is the closest to what we want. Okay, so this is what we want, to run it in GUI mode. Okay, so this is going to be running in GUI mode. Load the program into RAM. It's called struct.csv, and then we just run it. Control K. It's done. All right. Now that it's done, how do we know whether the program worked or not? Okay. Zoom in first because I know you guys cannot see the numbers. Nope. There we go. Okay, get back here. Look into the RAM component. And we focus on the last portion of RAM. So, do you think the program is working? Where's my var1, by the way?
At the 7 from.
It's the highest 7 bytes. Because var1 got allocated first, which means it is at the very top of the stack, right? how big is var1? How many bytes is it supposed to take up? 7 bytes. Okay, very good. So let's count. 1, 2, 3, 4, 5, 6, 7. These are the 7 bytes. That is var1. Okay. How did we initialize that var1? Remember, x is the first one. It's supposed to get a 10, which is a in hexadecimal. The first byte of the array by is supposed to be 0, but it was 0 to begin with, so it remains as a 0. And in Z, which is the last member, is supposed to get 15, which is 0f in hexadecimal. So it did get initialized correctly. Okay? Now, just because the subroutine works doesn't mean that I cleaned up the stack properly and did everything else correctly. So the other thing I also need to check is going to be the register bank and make sure that register D is 0. Because the stack pointer is supposed to be balanced, which means whatever it starts off with is whatever it should end up with. So let's go ahead and take a look at the stack pointer, which is just register D. And very convenient to be able to see it this way. You know, the previous version of the processor doesn't bring out the values of the registers, but we can see the register D is 0, so the stack is balanced. One more thing to check. Am I stopping at the right halt instruction? There's only one halt instruction, but it doesn't hurt to check. So that is controlled by the program counter. PC is 18 in hexadecimal. So when we go back to the assembler, now in the assembler, one particular tab is useful for debugging purposes, especially if you have a trace analyzer. It is the tab that is named source debug. So if you go to the tabs and look up source debug, because it has the original code, including the comments on one side, and then the location of that code on the other side in hexadecimal, which makes it very handy. So we can see that the halt instruction has an address of 17, but in the emulator, in Logic it is 18. Why? What makes program counter 18 instead of 17 when we execute the halt instruction? Because the decode cycle auto increments the program counter. And the decode cycle happens before we execute the instruction. So by the time we execute the instruction, the program counter is already 1 past the address of the instruction that we execute. So PC being 18 is consistent with the halt instruction at location 17. So as far as those simple checks are concerned, the program did work. Now, did it mean that I did not mess up somewhere else? You know, no, I could have messed up something else. But as far as the effect of the program is concerned, I could tell that it's working correctly. So the program that you guys are supposed to work on tonight, you know, with the lab, is combining recursion, structures, pointers, subroutine calls. It's combining all of those things together, which means you have 1 week to work on it. So I wouldn't rush it. I would make sure that all the concepts are understood correctly first before getting started with that program. Okay? So here's the program, because I know some of you will ask me about the access code. So let me look it up first, because I cannot remember either. And yes, this assignment is only worth 4 points. Even I realize it's only worth 4 points. But is it worth doing? Well, that's up to you guys to decide. It's struct, the access code is struct, and you have 1 week to work on it.